Hello student, I am Professor Jayanta Chopde, working in Electronics and Telecommunication Department. I would like to welcome to this lecture on Laplace transform. Now in last lecture, we studied the different types of the systems, and in that the continuous time and the discrete time system, causal and non-causal system, static, dynamic system, time invariant, time variant system, then linear, non-linear system, stable and unstable system. And in this lecture, we are going to study the definition of the Laplace transform, definition of the inverse Laplace transform, then convergence of the Laplace transform, that is the region of convergence of the Laplace transform, then what is the S plane and what is the poles and the zeros of the system, and the unilateral Laplace transform. Now, before starting the content delivery, we will discuss what is the transform and why the transform is used. Now we know that the signal, or the definition of the signal is the function of one or more independent variable that carries the certain information, or typically it carries some information, is called as the signal. Means it is function of the one or two independent variable, and mostly that independent variable is time. And if we are representing the signal with respect to time, and this is the physical parameters, then this domain is called as the time domain. In many time, it is very difficult to analyze that signal in time domain. Hence, we convert that time domain signal into another domain, and when we convert that signal into another domain, that is called as the transform. Means transformation of the original signal into another domain. And in that domain, we will carry out the analysis of that signal, and again we will convert that signal into original signal. And in UG program, the most well-known transforms are the Laplace transform and the Fourier transform. The Fourier transform and the Laplace transform. In case of the Fourier transform, we are converting the time domain, or transform the time domain into frequency domain. While in case of the Laplace transform, the time domain into S domain. Now the both transforms are used to solve the differential equation. Now if we have to solve the differential equation using the classical method, then it takes more time, because to solve this differential equation using the classical method, you have to convert that, or first you have to find out the complementary function, then particular integral, substitute the boundary conditions, and after that, to get the final answer, we have to add the both solution, complete CF plus PI. Again, to find out the PI, first we have to identify whether this is homogeneous equation, non-homogeneous equation, which types of the differential equation, and it is tedious, time consuming task. Hence, instead of that, using the transform, we can easily solve the differential equation. Now, how we will solve this differential equation using this transform? First, we will convert the differential equation into algebraic equation. Now, in case of the Fourier transform, this algebraic equation is in frequency domain, and in case of Laplace transform, the algebraic equation is in S domain. And then the result is finally transformed to the time domain by taking the inverse of the Fourier transform and the inverse of the Laplace transform. But to solve the differential equation using the Fourier transform is rarely used, because the Fourier transform does not exist for many signals, and the Fourier transform cannot be used to analyze the unstable system. Hence, this alternative approach to redefine the transform and include the exponential conversion factor sigma along with j omega. As the Fourier transform is represented in terms of in frequency domain, mean that is j omega, and the alternative approach is the redefine the transform, and that include the convergence factor sigma and j omega. This Laplace transform is named after the great French mathematician and astronomer Laplace, who first presented this transform and its application to differential equation. And this signal xt is represent, in case of the Laplace transform, the signal xt is represent as the sum of the complex exponential of the form e raised to st. Yes, S is sigma plus j omega. And for the Fourier transform, the signal xt is represented as the sum of the complex exponential of the form e raised to j omega. Means this transform is nothing but conversion of that from one domain into another domain. If we are transform this signal from t to s domain, this is the Laplace transform, and if we transform that signal from time domain into frequency domain, then it is the Fourier transform. Then next one is the definition of the Laplace transform. And what are the application of the Laplace transform? Using the Laplace transform, we can solve the differential equation. This is the beauty of the Laplace transform. Also, we can analyze the unstable system. And the Laplace transform can be used to analyze the signal or the function which is not absolutely integrable. The signal which is called as absolutely integrable, when we integrate this signal over the entire period, that is from minus infinity to plus infinity, this should be less than infinity. Then how will represent this Laplace transform using the mathematical equation? We know that this equation 1 is the representation of the signal in frequency domain, and that is called as the Fourier transform. That is x of j omega, that equal to minus infinity to plus infinity x of t e raised to minus j omega t. This is the Fourier transform of x of t. And the equation 2 is the inverse Fourier transform of this frequency domain signal x of j omega, that is 1 upon 2 pi minus infinity to plus infinity x of j omega e raised to j omega t d omega. Now replacing j omega by sigma plus j omega, in equation 1 and in equation 2, we are getting this equation 3a and 3b. Replace the j omega by sigma plus j omega. Here j omega is sigma plus j omega t dt, and here this. Now as we know that s equal to sigma plus j omega, we substitute s equal to sigma plus j omega in equation 3a. In 3a, that time we are getting this one is e raised to minus s t, and this is x of s. In this equation 3a becomes x of s is equal to minus infinity to plus infinity x of t e raised to minus st dt. This is the Laplace transform. This equation is the representation of the xt signal in x of s domain, that is the Laplace transform of the x of t. Then the inverse Laplace transform equation is obtained using the 3b equation. We substitute s equal to sigma plus j omega, and this integration is with respect to d omega. Hence it convert into with respect to ds. For that, if we integrate this equation sigma plus j omega equal to s, then this is constant, in differentiation of this one is constant, d omega that equal to 1 upon j ds. Means instead of d omega, this is ds by j 1 upon 2 pi as it is, and change the limit. This is s equal to sigma plus j omega. When omega tends to minus infinity, this becomes sigma minus j infinity, and when this is plus infinity, this is sigma plus j, this sigma minus j infinity to sigma plus j infinity x of s e raised to st ds. This is the equation to find out the inverse for Laplace transform. But generally this equation is not used because this is the complex equation. Hence to find out the inverse Laplace transform, we are using the another method, and that method is called the Heaviside theorem. The symbol for the Laplace transform is like this, or we will simply write this EL, and meaning of this x of t, Laplace transform of this is x of s, and the inverse Laplace transform of x of s is x of t. Hence this directions is the bidirectional, or the Laplace transform of x of t that equal to x of s, and the inverse Laplace, this is minus 1 means this is the inverse Laplace of x of s equal to x of t. Then the convergence of the Laplace transform means here we will find out the region of convergence. As we know that we cannot find out the Fourier transform for the signal which is not absolutely integrable, but we can find out the Laplace transform of that signal which is not absolutely integrable, and for that we will find out the range of the sigma where that transform will converge. Now here this equation is the bilateral Laplace transform equation. Bilateral means from minus infinity to plus infinity, and unilateral means from 0 to infinity. There are two types of Laplace transform. First one is the unilateral and second one is the bilateral. Then if we substitute s equal to sigma plus j omega, then we are getting this equation is x of t e raised to minus sigma t e raised to minus j omega t. If we compare this side to the Fourier transform, then the Fourier transform is e raised to minus j omega t dt. xt is there, e raised to minus j omega t dt, and this is this equation is the Fourier transform of the x of t. Now here, in case of the Laplace transform, instead of x of t, this is the x of t into e raised to minus sigma t. Means the equation to indicate that the Laplace transform is the Fourier transform of x of t e raised to minus sigma t. And the necessary condition for the convergence of the Laplace transform is the absolutely integrability of the x of t e raised to minus sigma t. Now in case of the Fourier transform, this should be absolutely integrable, means the signal should be absolutely integrable. Minus infinity to plus infinity xt dt. This should be less than infinity. If this is not, this condition is not satisfied, we cannot find out the Fourier transform. But in case of the Laplace transform, now the x of t, that is x of t into e raised to minus sigma t dt. Now this should be less than infinity. For that purpose, we will find out the range of this factor sigma for which the Laplace transform is converge. Means we can find out the solution of that is known as the region of convergence or the ROC. Now we will take the one example that will clear what is the region of convergence. Now consider the signal e raised to 2t ut. Ut means that signal is exists for only positive value of t. Means t is greater than or equal to 0. Now for t equal to 0, this is e raised to 0, means this amplitude is 1, and as t is increasing, the amplitude of the signal is increasing, and at t tends to infinity, the signal is e raised to infinity, and that equal to infinity. Means this signal is not absolutely integrable. And the Fourier transform of the signal does not exist. We cannot find out the Fourier transform because it is not absolutely integrable. But we can find out the Laplace transform, and we will find out the range of the sigma where that signal is absolutely integrable, or that signal is converge. Hence, we will multiply the signal e raised to minus sigma t, as in case of the Laplace transform, we are finding out instead of x of t, this is x of t into e raised to minus sigma t. Then the resultant signal is xt into e raised to minus sigma t, and the xt is e raised to 2t e raised to minus sigma t multiplied by these two. Then resultant signal is this. Now here the t is positive values for this. This is e raised to 2 minus sigma t. T is positives. If t is infinity, if we consider this is infinity, then 2 minus sigma, and if this is positive, 2 minus sigma is positive, that time what will happen? This positive, this becomes positive, right? And this is not absolutely integrable, but if this term 2 minus sigma is negative, is less than 0, then this 2 is less than sigma, means sigma is greater than 2. When the sigma is greater than 2, that time this term is negative. The equation is like this. If we consider this sigma value is 3, then this is 2 minus 3 and t. This is e raised to minus t. Now at t equal to infinity, this signal is, the amplitude of this one is 0. This is not infinite, and this is absolutely integrable for sigma is greater than 2. Hence the range of this sigma value, is called a region of convergence. Means the region of convergence for this signal, the region of convergence for this signal is for sigma is greater than 2. Then what is S plane? As S is the complex variable and denote is variable and defined by S equal to sigma plus j omega, where the sigma is the real part and omega is the imaginary part of the earth domain, and this is the earth domain and the real part is along this x-axis and the imaginary part is along y-axis, and this S equal to sigma plus j omega. This is minus infinity, this is plus infinity for the real part, and this plane is called as the left hand side plane, left hand plane, and this is called as the right hand plane or right hand side plane. Now the left hand side plane is occur for sigma is ranging from minus infinity to 0, and this is from 0 to infinity, and this is from minus infinity to 0, and this is called as the S plane. Now the more general form of the Laplace transform is the ratio of the two polynomial, this numerator divided by denominator. Means the Laplace transform is represent like this. If we consider this is s raised to 3 plus s square plus 2s polynomial equation plus 1 divided by s square plus 2s plus 3 like this. This is same. These are the constant bm, bm minus 1, b1, b0. Similarly here in denominator these a1, a0, these are the constant, and this is the power of this s. And from this equation we will define the zeros of this system and the poles of the system. Now when this numerator value becomes 0, that time we will equate this numerator equal to 0. We will solve or we will simplify this equation by taking this bm constant, then we are getting this next equation like this. This bm equal to m, this product term k equal to 1 to m s minus zk. Meaning of this is if this one is equation 3s plus 2, this equation, then here we are writing this equation in terms of take the factor of this s 2 1 s plus 2 s plus 1 like this, and equate this equal to 0 and find out the s value where this function becomes 0 is called as the zeros of the system, and the symbol for the 0 is like this. Then what is pole of the system? Pole is the function, this function Laplace transform where this function is infinite, that is called as the poles of that system, or the critical frequency at which that function becomes infinity is called as the poles of the system, and the critical frequency where this function becomes the 0 is called as the zeros of that system. Now here to find out the pole, equate the denominator to 0 and find out this in terms of this product term, and this critical frequency s equal to pk, that is s equal to p1, s equal to p2. This is called as the poles of this system, and this symbol for this pole is like this, or the poles is represented using this symbol and 0 is represented using this symbol. Now we will solve some problem. We will find out the Laplace transform of some signal and the ROC of that signal. Now the first signal, is x of t e raised to minus at ut. Now what is meaning of this ut? Ut means that signal is exist only for the positive value of t is greater than or equal to 0. Means by definition of this Laplace transform, we will write this is x of s that equal to minus infinity to plus infinity x of t e raised to minus st dt. But x of t is given, that is minus infinity to plus infinity e raised to minus at ut e raised to minus st dt. As we know that ut is exist only for the positive value of t, and this positive value of the t, that time the integration limit become from 0 to infinity. So we write this is 0 to infinity e raised to minus at e raised to minus st dt. Means here we will write this is 0 to infinity e raised to minus a plus s t into dt. Now first we will find out the region of convergence of this equation, or for this signal, as x of s that equal to 0 to infinity e raised to minus a plus s t into dt. Now this integration is from 0 to t, means for the positive value of this t, and here when the t is infinity, t is infinity means positive value, this is minus sign, means a plus s, if this one is negative, if a plus s is negative, means less than 0, that time what happens, this negative becomes positive, and this positive means this becomes e raised to infinity, and that is infinity. Now here we will find out the range where that signal is absolutely integrable. Here the signal is not absolutely integrable. Now for that, the condition is that in this case this a plus s should be, this is positive, this also should be positive, means that should be greater than 0. When this is positive, means that is total is minus, and that signal is absolutely integrable. Means we can say that yes, real part of s should be greater than minus a. And what is the real part? Sigma. Sigma should be greater than minus a. Means we will define this region of convergence on s plane j omega. This is minus a. Means that function is absolutely integrable for the sigma value, and for the sigma value should be greater than minus a. This is called as the ROC of the signal. Sigma is greater than minus a. Then find out this integration x of s that equal to, this is 0 to infinity e raised to minus a plus s t into dt, and this integration is 1 upon minus a plus s into e raised to minus a plus s t, and substitute the limit 0 to infinity. When this is infinity, e raised to minus infinity is 1. So e raised to, this is minus infinity means 1 upon e raised to infinity means 1 upon infinity, means this term becomes 0. And for 0, this is minus 1 upon a plus s into e raised to 0 is 1, means the Laplace transform of this signal is 1 upon s plus a. And the ROC is sigma is greater than minus a. Then the second signal x of t that equal to minus e raised to minus at u of minus t non-causal. See, this is minus ut, means this is folding of this ut signal, and that signal will exist from minus infinity to 0. Ut signal is like this. This is u of minus t, and for ut signal limit is 0 to infinity. This is minus infinity to 0. And so we will write this x of s that equal to minus infinity to plus infinity, x of t e raised to minus st dt. This is by definition of the Laplace transform. Now as this is the non-causal sequence, this is minus infinity to 0, this is minus e raised to minus at, u of minus t means this limit is changed here, into e raised to minus st dt. Now we will absorb this negative sign by interchanging this integration limit, that is 0 to minus infinity e raised to minus e raised to minus a plus s t dt. Now this term is same as the previous problem, but here the limit is minus infinity, and if we substitute this limit, this is this term a plus s and this t, and t is minus infinity, then this minus infinity and minus infinity become plus infinity, and again if this term is plus, then this is e raised to infinity, and e raised to infinity is infinity, and that signal is not absolutely integrable. Hence the condition is that the a plus s should be less than 0. If this one is negative, then this negative becomes positive, again this negative multiplied this negative means this one is negative, and that signal is absolutely integrable, means s is less than minus a, and s is the real part of s that equal to sigma, and sigma should be less than minus a. In the region of convergence, sigma, this is j omega, this is minus a, means this signal is absolutely integrable, or we can find out the Fourier transform, Laplace transform of the signal for sigma is less than minus a. Sigma is less than minus a is the region of convergence. Then solve this to find out the Laplace transform x of s that equal to 0 to minus infinity e raised to minus a plus s t dt. Take this integration and substitute the limit. Is here the integration is, or after solving this we are getting this is s plus a. Now here if we observe these two problems, the first problem is the causal and second one is the non-causal. The Laplace transform of the first one is 1 upon s plus a, and for the non-causal sequence also the Laplace transform is same, s plus a. The change is that the region of conversion for this is when sigma is greater than minus a, and for this non-causal this is less than minus a. Means we can, in general we can say that the region of convergence ROC for causal sequence or causal signal is RES is greater than A or alpha, and ROC region of convergence for non-causal signal is less than A. Now find the Laplace transform of the ROC of this following signal, this signal. Now here the two signals are added. As we know that both signals are here the causal sequence. Hence we directly write this x of s that equal to minus infinity to plus infinity x of t e raised to minus st dt. Now here both are causal, means this limit change from 0 to infinity, and add these two signal e raised to minus 3t plus e raised to minus 2t into e raised to minus st dt. We will separate out this 0 to infinity e raised to minus 3t e raised to minus st dt plus second term 0 to infinity e raised to minus 3t e raised to minus 2t dt. Here this is 0 to infinity e raised to minus 3 plus st dt plus 0 to infinity e raised to t e raised to minus st minus 2 plus st dt. Now here for first term as well as for the second term, the t is infinity here. Means if we consider for the first e raised to minus 3 plus s into t, and if this one is infinity positive value, this is negative, means 3 plus s should be positive. Means when 3 plus s is greater than 0, that time this negative, this is positive, that becomes negative, and that signal is absolutely integrable. Means this sigma, this real part, we will write this is s should be greater than minus 3. S should be greater than minus 3, and s is the real part of s is sigma, means sigma should be greater than minus 3 for first term. Similarly for the second term, this sigma should be greater than minus 2. This is minus 2, this is minus 3, greater than this, and this one is greater than this. Now here note both the terms converge for the ROC. Both terms, this first term is greater than minus 2, minus 3, and second one is greater than minus 2. Means the both terms converge for the ROC is sigma is greater than minus 2. This first as well as the second, in the region of convergence for this is minus 2. And we know that for e raised to minus at, the Laplace transform is s plus a. In the Laplace transform for this, or we will solve this. After solving this first term and the second term, find out the Laplace transform, that is 0 to infinity e raised to minus s plus 3 t dt plus 0 to infinity e raised to minus s plus 2 t dt. Take the integration of this first term, and this is minus s plus 3 0 to infinity plus minus 1 upon s plus 2 e raised to minus s plus 2 into t. This is 0 to infinity. Now substitute this value. After substituting the upper limit and the lower limit, we are getting this is s plus 3 plus 1 upon s plus 2. Means the Laplace transform of that signal is x plus 3 and plus 1 upon x plus 2. Find the Laplace transform of the ROC and the ROC of the following signal, this signal. Now if you observe this signal, again this signal is consisted of x1t and this is x2t. But now the x1t and the x2t, one signal is causal signal and another one is the non-causal signal. In previous case, both signals were the non-causal signals. Now by definition of this Laplace transform, x of s that equal to minus infinity to plus infinity x of t e raised to minus st dt. What is x of t? Minus infinity to plus infinity. This is e raised to minus at ut plus addition of these two signal bt u of minus t into e raised to minus st dt. Now this is the causal, first term is the causal and second one is the non-causal. Hence for the first term the limit is from 0 to infinity and for second minus infinity to 0. Means we will rewrite this equation 0 to infinity for first term e raised to minus at ut means 0 to infinity e raised to minus st dt plus for the second minus infinity to 0 e raised to minus bt e raised to minus st dt. Means simplifying this equation, we are getting this is e raised to minus, take common, this is s plus a t dt plus minus infinity to 0 e raised to minus s plus b t into dt. Now I will rewrite this equation here, x of s that equal to 0 to infinity e raised to minus a plus s t dt plus minus infinity to 0 e raised to minus s plus b t dt. This is also s plus a. Now here we will find out the region of conversion for the first term and for the second term. Now here for first term t is positive, and if we substitute this t is infinity here, is for s e raised to minus s plus a into infinity. This is negative, means s plus a should be positive, means for the first term s plus a should be greater than 0. For the second, if you substitute here, this one is in minus infinity, the limit is maximum limit is minus infinity, this is minus infinity, this minus minus become plus, And if this one is s plus b is positive, that time this is not absolutely integrable. Mean this term s plus b should be less than 0. Means s should be greater than minus a. And what is s? S is the real part of the s is sigma, that is minus greater than minus a is the region of conversion for this first term. And for this s should be less than minus b, and the real part of s is sigma. Sigma should be less than minus b. Means we will draw the region of conversion on s plane. This is sigma minus sigma j omega. For this is greater than minus a, and for this is less than minus b. This is minus a. Means we can say this region of conversion for the first one is greater than minus a, and for the second term is this one is less than minus b. Mean the region of conversion is greater than minus a and less than minus b. The next one is find out the Laplace transform of this above term, that is x of s that equal to 0 to infinity e raised to minus a plus s t dt plus minus infinity to 0 e raised to minus b plus s t dt. Now take this integration, that is minus 1 upon a plus s e raised to minus a plus s t, and limit is 0 to infinity, plus minus 1 upon b plus s into e raised to minus b plus s t, and limit is from minus infinity to 0. And after substituting this limit and simplifying this, as we know that e raised to 0 is 1 and e raised to minus infinity is 1 upon e raised to infinity, and that equal to 0. That after substituting this, we are getting this result is 1 upon s plus a minus 1 upon s plus b. X of s that equal to 1 upon s plus a minus 1 upon s plus b, and here the signal is e raised to minus at ut, and this is plus e raised to minus bt u of minus t. One is causal and another is non-causal. Now we know that this is Laplace transform of e raised to minus at. If this one is negative, then this is positive, s plus a. If this is positive, then this becomes negative. Similarly, if this one is plus, this becomes negative. If this one is minus, this becomes positive. Then the unilateral Laplace transform. The unilateral Laplace transform is applied to the signal that are causal, means from 0 to infinity. The unilateral Laplace transform of the signal xt is defined as only this integration limit will change, that is 0 to infinity. This is x of t e raised to minus st dt. And this is the same as the bilateral Laplace transform, only the limit is changed from 0 to infinity instead of minus infinity to plus infinity. And instead of xt signal, the signal is xt into e raised to minus sigma t in case of the unilateral Laplace transform, and that signal should be absolutely integrable for this limit 0 to infinity. Now find the unilateral Laplace transform of the following signal. Now first signal is the delta t, delta function. By the definition of the Laplace transform, we write this is 0 to infinity for unilateral Laplace transform. This is xt e raised to minus st dt, and that equal to 0 to infinity del t e raised to minus st. This signal will exist at t equal to 0. As the signal is exist only for t equal to 0, we will write this is t equal to 0 to infinity del t e raised to minus 0, substitute t equal to 0 dt, and that equal to 0 del t into 1 into dt, and here integration del t means area under the delta function is 1, and this is 1, means here this sigma, the ROC is the entire this sigma value, entire S plane. The second signal is ut, means this is the step function. Second function x of t that equal to ut. Now by definition of the Laplace transform, this is 0 to infinity, as this is unilateral. This x of t e raised to minus st dt that equal to 0 to infinity ut e raised to minus st dt. Ut value is 1, unit ramp function amplitude, and if we substitute the amplitude is 1, then this is 0 to infinity 1 into e raised to minus st dt. Now this is negative. If t is positive means s should be negative, means for this is s should be positive, and for means real part of s, this should be greater than 0. See here, this is e raised to minus st, t is positive, infinity, this is negative, and again if s is negative, that time this negative becomes positive, and that signal is not absolutely integrable. And the ROC for that is that signal should be greater than 0, means that should be positive, and this sigma should be greater than 0. Mean the region of conversion, this is sigma, that should be greater than 0, is this ROC. Then take the integration, this is e raised to minus s t dt that equal to minus 1 upon s e raised to minus st, and substitute the limit 0 to infinity. E raised to minus infinity, this term becomes 0, and this means 0 minus this minus 1 upon s and e raised to 0, that is 1 upon s, means the Laplace transform of the ut is 1 upon s. Then find the Laplace transform and the ROC of the following signal, and these are the assignment question. And the fourth question, x of t that equal to cos of omega 0 t, and answer for this x of s that equal to s upon s square plus omega 0 square. Find out the Laplace transform of this all these four signals and the ROC. Now in this lecture we discuss what is the transform, what is the difference between the Fourier transform and the Laplace transform, what are the drawback of the Fourier transform, where this Laplace transform is used, definition of the Laplace transform, definition of the inverse Laplace transform, then what is the S-plane, then the unilateral Laplace transform, and we have find out the Laplace transform of the causal and the non-causal signals. Thank you. We will stop here.